The fourth kinematic equation in the x direction was Vx squared equals V naught x squared plus 2ax x minus x naught. And there's that term right there, ax x minus x naught. Let's solve this equation for that term. We'll bring the V naught x squared to the other side and divide by 2. We end up with then ax x minus x naught equals, dividing by 2, 1/2 Vx squared minus 1/2 V naught x squared. Let's take this term and stick it in here for the ax times x minus x naught. What do we get? We get W net, the net work, is equal to m times that quantity. So m times this. In other words, 1/2 mvx squared minus 1/2 mv naught x squared. We derived this assuming that delta x was in this, that delta r was in the x direction. But for a general direction where we want to define delta r as being in some random direction, not along the x-axis, basically we get this same result, but we have the magnitude of the velocity squared and the magnitude of v naught squared. So we can write this then as w. Let's remember, this is the net work done. The total work done on the object is equal to 1/2 mv squared minus 1/2 mv naught squared. This is a very, very interesting result. Let's take a look at this. First of all, let's notice over here, we have 1/2 mv squared minus 1/2 mv naught squared. That is the same quantity, 1/2 mv squared, but evaluated at two different points in the motion. 1/2 mv squared evaluated finally, and 1/2 mv squared evaluated initially. Well, what is this thing? It's a quantity that deals with the motion of an object. Let's imagine we have an object of 4 kilograms moving at 3 meters per second. This gives us some quantity associated with the motion. In other words, let's figure this out. 1/2 times m, which would be 4 kilograms, times v, which is 3 meters per second, squared. Well, what do we get? 3 squared is 9, 1/2 times 4 is 2, 2 times 9 is 18. 18. And then what are the units? Let's see, we have kilograms. We have meters per second squared, which gives us meters squared per second squared. We get kilogram meters squared per second squared, but we know that's a joule. Which makes sense, because we would expect the units of this side to be the same as the units of this side, and we know the units of this side are the units of work, so that has to be joules. So we end up with this quantity as 18 joules. This is a quantity that deals with the motion of the object. It's something that pertains to how massive the object it is, how massive it is, how fast it's moving. The more massive the object it is, the more massive it is, the bigger this thing is, the faster it's moving, the bigger it is. Well, this quantity is a very, very important quantity that we are going to see often. And this 1/2 mv squared is what we call the kinetic energy. The kinetic energy of the object. Kinetic, in terms of motion, it is an energy of motion. It's how much energy the object has because it's moving. If the object were stationary, V would be 0, and the object would have 0 kinetic energy. So the object only has kinetic energy if it is moving. Stationary objects have 0 kinetic energy. Very, very interesting. Let's rewrite this result, and just let's put in the kinetic energy rather than 1/2 mv squared. With the total work done equal to 1/2 mv squared minus 1/2 mv naught squared, and 1/2 mv squared being the kinetic energy, which I'll write as KE for short, so KE for kinetic energy. What we have is that the total work done, the net work, is equal to 1/2 mv squared, that's the final kinetic energy, minus 1/2 mv naught squared, that's the initial kinetic energy. So we have the final minus initial kinetic energy, which we can write as delta KE, the change in the kinetic energy. This is what we call the work-energy theorem. What is this telling us? When we do, or when an object has work, a net work, total work done on it, that work goes into changing the kinetic energy of the object. Doing work on an object, and I mean the net work done. Doing work on an object goes into changing that object's kinetic energy. For example, very simply, if I have a pen, if I do work on it and I apply a force on it, what happens? As I push that object through a distance, I'm doing work on that object, I am increasing its kinetic energy. The kinetic energy goes up, and what happens? It flies off. What if we did negative work on an object? Imagine that there's a car rolling toward you, and you push on that car, and as that car moves forward, you have to move backwards to stop it. You are now applying a force in this direction, and the motion is in this direction. So the angle between them is 180 degrees, the work done is negative. What happens to the kinetic energy? As you are pushing on the car in the opposite direction, the car slows down. The kinetic energy decreases, so that the final kinetic is less than the initial kinetic, and delta KE will be negative. So doing positive work on an object increases its kinetic energy. Doing negative work on the object decreases its kinetic energy. Doing zero work on an object maintains its kinetic energy. In other words, the kinetic energy will remain constant. Very good. Let's stick some numbers in here. Let's imagine we have a person here pushing on a box, and I put this box on wheels. So let's ignore friction for the moment. Let's assume there's no friction on the box. The person pushes to the right with a force of 25 newtons, and let's imagine it's a 100-kilogram box and it starts from rest. Let's figure out, if this person pushes on the box for 10 meters, what's the final velocity of the box? But let's solve this using the work-energy theorem. Let me ask you, could we solve this using Newton's laws? Well, we know the force, we know the mass, we could figure out the acceleration, we could figure out, knowing the initial velocity, we could figure out the final velocity. Yes, we could. But let's not do that. Let's solve this using the work-energy theorem. So what do we know? Well, let's think about this. We want the final velocity. Where is the final velocity in the work-energy theorem? The final velocity is in the final kinetic energy. So if we could find the final kinetic energy, we'd be able to solve that for the final velocity. To find the final velocity, we need the work and the initial kinetic energy. We can find the initial kinetic energy, and we can find the work, the net work done on the object. So let's do it like that. First of all, what's the initial kinetic energy? The initial kinetic energy is 1/2 mv initial squared. Assuming that it starts from rest, the initial velocity is 0. So what's the initial kinetic energy? It's 0. So our initial kinetic energy is 0. What is the work done? How much work is done? Remember, work is the net work. Well, what forces are acting on this object? We've got this pushing force of 25 newtons. What other forces are there? Well, there's the normal force. There's the weight. Weight W, not work. Notice that the normal force and the weight will cancel each other out. They are also not doing any work, so we don't have to worry about those. The only work being done is by the pushing force. So how much work does the pushing force do? Well, what is work? Work is F delta R cos theta. What is the force? 25 newtons. What is delta R? It's moving 10 meters. Cosine Theta, what's theta? Theta is the angle between the force and the displacement. They are in the same direction in this case, so theta is 0, cosine of 0 degrees. Cos 0 is 1. So we have 25 times 10, or 250 Newton meters, which is a joule. There we go. What do we have so far? We've got the total work done, 250 joules, is equal to the final kinetic energy, that's what we're looking for, minus the initial kinetic energy, and the initial kinetic energy is 0. So we have the final kinetic energy is 250 joules. But that is equal to 1/2 mv final squared. We know the mass, we can solve for the final velocity. Multiply by 2, divide by m, take the square root, we have v is equal to 2 times 250 joules, 2 times 250 joules, divided by m is 100 kilograms. This is v squared, so we take the square root. There we go. Multiply that all out, and what do we get? We get v is 2.24 joules per kilogram. Remember, a joule is a kilogram meter squared per second squared. Divide off the kilograms, we get meters squared per second squared. Take the square root, meters per second. Just as we would expect for the velocity. And once again, if you can't remember all those unit definitions, just remember, as long as you put everything in SI units, you should get your final unit as the SI unit for the quantity you're looking for. If you're taking a quiz or an exam or something like that, and you're really pressed for time, you might take a little shortcut like that. However, keeping track of all of your units as you go along is one little way of checking to make sure you didn't make a mistake. If you go through a calculation and end up with the wrong units, you know you must have made a mistake somewhere, and you could go back and hopefully find where you made that mistake. But if you kind of ignore the units and just stick on the correct units at the very end, you might make a mistake and not have realized it because of those units. So it's just as a side note. But we do get the correct unit, so hopefully we did not make a mistake. And there is our final answer, 2.24 meters per second. As I said, could we have done that with Newton's laws? Yes, we could. And I would suggest that you try that. Try using Newton's laws and see that you get the same answer. Excellent. Let's take a look at a couple more examples. Here's an example that I really like. First of all, it's just in general an interesting example, but it's astronomical, and I really, really like astronomy. I was actually a physics astronomy major when I was in college. Let's imagine we've got a satellite going around the Earth. This is very similar to an example we talked about last time when we were looking at uniform circular motion. Let's imagine that the satellite is in a circular orbit around the Earth. Let's figure out how much work is done on the satellite due to whatever forces are acting on it. What force is acting on the satellite as it goes around in its circular orbit? Well, the only force, assuming we can ignore any resistance moving through whatever very, very thin atmosphere there is up there, the only force acting on it is the gravitational attraction from the Earth. So the gravitational force pulling the satellite down towards the Earth. How much work does that force do on the satellite? Let's think about that for a second. And I really want you to think about this. You might even turn the video off to think about it. I'll assume that you did that. What's the displacement? As the object moves around the circle, the displacement is always in the direction of the velocity. So how much work is done? Zero. Zero work is done. Why? Because the displacement, the velocity, displacement and velocity are in the same direction, are always perpendicular to the force. The force, the gravity, is a centripetal force, which is towards the center of the circle, towards the Earth, while the velocity is always tangent to the circle, which is perpendicular to the central line. The angle between them is 90 degrees. Cosine of 90 is 0. Zero work is done. What does that tell us about the kinetic energy? Remember, from the work energy theorem, the total work done is the change in the kinetic energy if the net work done is 0, the kinetic energy, it doesn't mean it's 0, it means it doesn't change. Delta KE is 0. That means the kinetic energy is constant. If the kinetic energy is constant, that means the velocity, I should say the magnitude of the velocity, the speed is constant, which means the satellite is going to go around at a uniform speed, but we already talked about that. That is the condition of uniform circular motion. So the fact that we have a centripetal force, we can see then, means that we'll have a constant speed as it goes around in a circle. Because that force never does any work on the object, always being perpendicular to the displacement. There are other kinds of orbits, one of which, not a circular orbit, but an elliptical orbit. In other words, the satellite could be orbiting around the Earth in an ellipse. Now, I've drawn a very greatly exaggerated ellipse where it's very long. The Earth in an elliptical orbit, or anytime something has an elliptical orbit, the gravitating body is not at the center of the ellipse, but it's at one of the foci. An ellipse has 2 points that are called a focus, 2 foci. The plural of focus is foci. The Earth is at one of the foci, and the satellite then orbits around with the Earth at that point of the ellipse. Let's think about this. Let's imagine our satellite is up here. What kind of effect is the force going to have in this case? Well, the displacement, again, is tangent to the orbit, while the force is always toward the Earth. Well, in this case, the force and the displacement are not perpendicular. We notice there the angle between them is less than 90 degrees. Because it's less than 90 degrees, cosine of an angle less than 90 degrees is positive. It's greater than 0. In this case, the work done is going to be positive. If the work is positive, that means the kinetic energy is increasing. In other words, the velocity is increasing. So what we have is from this point in the orbit to this point in the orbit, the satellite is going to be speeding up. So it's going to be speeding up and going faster. However, when it comes down to this point over here, or any part of this motion, let's notice the displacement is now in this direction. We're assuming it's going in a counterclockwise direction. While the force is that way. Notice now the angle between the force and the displacement is greater than 90 degrees. Cosine of an angle greater than 90 degrees, between 90 and 180, less than 180, and greater than 90, is a negative number. So in this case, the work done will be negative. What does that mean? A negative work means the kinetic energy is decreasing. Delta KE is negative. What does that mean? A decrease in kinetic energy means the speed is decreasing. The satellite is slowing down. So as the satellite goes from this point to this point, it's actually slowing down. So in this motion, we have the object speeding up and then slowing down. It's a little hard for me to do this, but I think you get the idea. Speeding up and then slowing down. Speeding up, slowing down. So the point over here is where the satellite is going the slowest. And the point over here is where the satellite is going the fastest. This point is where the satellite is farthest from the Earth. This point in an orbit around the Earth is called the apogee. The apogee point of the orbit. G, like geo, meaning Earth, apogee means farthest from the Earth. This point over here is where the object is closest to the Earth. And this is what we call perigee. Perigee, closest to the Earth. So the satellite then oscillates from its slowest point at apogee to its fastest point at perigee, speeding up as it goes from apogee to perigee, and then slowing down as it goes from perigee to apogee. Very, very interesting. We could actually have orbits, elliptical orbits around the sun, and in which case they are called aphelion for sun, so aphelion, and perihelion, the farthest point from the sun and the closest point to the sun in orbits that are going around the sun. Very, very good. Very interesting. Let's take a look at another type of work. Let's look at the work that is done by the gravitational force for an object moving under the influence of gravity. What kind of work does gravity do?